Hi Professor, myself Vishwanath. In this video, I'll be demonstrating my 10.2 HT task end-to-end project delivery. For this project, I built a complete machine learning model to detect cyber attacks using classical machine learning models. So here, I worked with two well-known intrusion detection datasets as per the assignment instructions. And throughout the process, I trained the models, tuned some parameters, generated the confusion matrices, and analyzed how each model behaves. So in the next few slides, I will walk you through what I did, the results that I have got, and the insights that I found. Yeah. The main purpose of this project was to understand how classical machine learning models perform when detecting the cyber attacks. So I wanted to see how the same model behave in two different environments. One is traditional network traffic and the other one is IoT sensor telemetry. To do this, I completed the full workflow. I cleaned and prepared both the datasets. I trained seven classical machine learning algorithms. Also, I generated accuracy scores, precision, recall, F1 scores, and confusion matrix for all the models. And in the end, I compared the results across both the datasets to understand why the models behave differently. So this point is important because cyber attacks are increasing across both IT and IoT systems. Organizations need lightweight and interpretable models, and through this project, I wanted to see which models are actually suitable for real world intrusion detection. Yeah. Here I have used two datasets that are widely used in intrusion detection research. The first one is NSL-KDD. It has 41 features and 5 attack categories like denial of service, probe, remote to locate, user to root, and normal traffic. So for the NSL-KDD dataset, it has both categorical and numerical features. And one of the biggest challenges I faced was the extreme imbalance. So remote to locate and user to root appear in very small numbers, which makes them very hard to classify. And the second data set is TANAIoT telemetry. It has 17 numerical features and over 4 lakh samples. This has only two classes that are normal and attack. So this dataset represents modern IoT environments, and because it's fully numerical and dense, it behaves very differently compared to the initial dataset NSL-KDD. Yeah. Now coming to the fourth slide, for the NSL-KDD dataset, I had to do quite a bit of pre-processing. So I removed the unused difficulty column, mapped all the raw attack names into 5 main categories, and label encoded the category features like protocol, service, and flag. After that, I standardized all the numerical features. So this step made a big difference, especially models like KNN, SVM, and logistic regression, which rely heavily on feature scaling. And for the second dataset, TANAIoT dataset, the pre-processing was much simpler because the dataset was already clean and numerical. So applied standard scalar and used 70-30 train test split to maintain the class balance. Overall, these pre-processing steps helped me avoid data leakage and ensured that all models were trained under fair and consistent conditions. Yeah, here are the models that I have used for this task. I trained 7 classical machine learning models for this project. So the first one is a logistic regression, a simple baseline model, and the second one is decision tree. It's good for interpretability. The third one, random forest. It's an ensemble method that usually performs well. And the fourth one is k-nearest neighbor. It's a distance-based model that benefits from scaling. And the fifth one, support vector machine. It's great for nonlinear boundaries. Sixth one, nav bias. It's a probabilistic model included as a benchmark. And the final one is gradient boosting, which I used only for the TANAIoT datasets because I found that it works well with the numerical telemetry data. So here, by using a mix of linear, tree-based, ensemble, and distance-based models, I was able to compare the wide range of learning behaviors. Yeah, and coming to the results, when I trained the models on NSL-KDD dataset, I got the accuracies in between 74 and 76% across almost all the models. So this is consistent with what other research papers report. The models performed well on the majority classes like normal, denial of service, and probe, but they struggled heavily with the remote to locate and user to root categories. Because these classes are extremely rare, the models barely got any correct predictions for them. Among all the models, I found that SVM, Decision Tree, and KNN gave the best balanced performance. Logistic regression also did well, but it reasonably worked. Naive Bayes performed the worst because its independencies assumptions don't match with the complex relationship in NSLKDD. And when I looked at the confusion matrix I generated, I could clearly see strong diagonals for the majority classes and almost no correct predictions for the R2L and user to root categories. Uh, And coming to the TAN-IoT dataset results, the best accuracy I got was from the KNN. It achieved 86.78%. So this makes sense because the dataset is fully numerical and dense, which suits distance-based models. A random forest also performed well with 81.92% accuracy. And decision tree gradient boosting were also strong. Logistic regression and naive Bayes did not perform well because the dataset contains nonlinear patterns so that these models cannot capture effectively. Overall, I would say TAN-IoT clearly favors the model that rely on distant matrices or ensemble decision boundaries. Yeah, and coming to the conclusion, when I compared both the datasets, I found that they behave very differently. NSLKDD is multi-class, imbalanced, and has overlapping patterns. So this makes it difficult for classical models to detect minority attacks like remote to locate and user to root. And coming to the second dataset, NIoT, it's binary and numerical. So it made much easier for models to separate the classes. So based on the results I got for the IoT intrusion detection, KNN and random forest are the most reliable choices. And for the initial dataset, NSLKD techniques like smart oversampling or class weight would help improve detection of minority classes. And coming to the future work, deep learning or hybrid ensemble approaches could improve performance across both the datasets. So overall, this point helped me understand how strongly the dataset characteristics influence the model behavior. Yeah, so that's all about it. Thank you.